This is Unit 2, Topic K. I accidentally have two Topic J's in here, so we'll make that a Topic K. And I'm looking now at derivatives of the inverse trig functions. Once again, if I don't know the derivatives of those functions, it's actually going to be easier for me to rewrite an inverse trig function, like y equals arctan x, as the related implicit function, and then do an implicit function to figure out the derivative that I want. So I'm going to take the tangent of both sides here. And that means that tangent y, tangent and arctangent are inverses, so that's just going to become x. And although it's an implicit function, it's a function that I know how to take the derivative of both sides now, which is a big advantage, right? So let's go ahead and do the derivative. The derivative of the tangent function is secant squared. So I'm going to get secant squared of y, and here's the chain rule, times dy dx, equals the derivative of x with respect to x is just 1. So dy dx is 1 over secant squared of y, and since the reciprocal of secant is cosine, that's just cosine squared y. All right, that's great, except originally we had an explicit function, so I'd really love to have this derivative not have a y in it. In order to fix that, what I'm going to have to do is use a little bit of right triangle trigonometry. Take a look at this statement right here, and let's draw a triangle for it. Think tangent y is, and I'm going to write it as x over 1. Tangent is opposite over adjacent. So I could draw a triangle where my angle here is the angle y, and x and 1 are the opposite and adjacent sides. Notice a little bit of Pythagorean theorem here, and the hypotenuse would be x squared plus 1 squared is still 1, square root of that. If I now use that picture, I can calculate the cosine of y just based on my picture. So let's do that. dy dx equals cosine y would be adjacent over hypotenuse, 1 over the square root of x squared plus 1. And then I want to square that. So dy dx ends up just being 1 over x squared plus 1. Nice explicit form, just has x's in the derivative now. You can actually do that same kind of analysis for any of the inverse trig functions, always just starting by turning them into a trig function that you know and doing an implicit derivative. That's all been done for us. And so the results are in this table down here. You can see the one that we did, the derivative of the arctangent, is right here. And then the rest of them are all listed for you as well. We will at this stage take this list as given. I know we only showed this one, but the other ones again are very similar, and we're going to go ahead and say, yep, this is our list of derivatives for the inverse trig functions. And let's just practice taking some derivatives using these through this list right here. So, in example 1, I want the derivative of the arc cosine of x cubed. So I'm going to start, maybe I should have left that up here. Let's see if I can get these all on the same screen. So I'm going to start by looking up my arc cosine derivative. and saying that I get negative 1 over the square root of 1 minus, and now I have to be a little bit careful because I didn't just have an x, I had an x cubed. So instead of x squared here, I would have that x cubed squared. Right? I'm using the pattern from the derivative, but substituting in my actual argument from the arc cosine function. Now there's also going to be a chain rule here. The derivative of x cubed would be 3x squared. So when all is said and done, I'd have negative 3x squared on top, and my denominator is the square root of 1 minus x to the 6th. All right, let's try another one. In number 2, we've got the derivative of e to the x arctangent 5x. So this is definitely a product. F would be e to the x, and g would be arctangent of 5x. F prime, nice and simple, still e to the x, right? G prime. I need the arctangent derivative, which here says 1 over 1 plus x squared. So I'd have a 1 over 1 plus, but again, I didn't just have x, I had 5x. So instead of x squared, I'm going to have 5x squared. Or 1 over 1 plus 25x squared. All right, we'll put our product rule together, fg prime plus gf prime. So fg prime, this is my dy dx now, would be e to the x times 1 over 1 plus 25x squared plus gf prime, e to the x times the arctangent of 5x. And there's not a whole heck of a lot you can do there. I guess we could factor out the e to the x if we wanted to, or we could simply put it on the top of the fraction. Again, there's nothing but cosmetic stuff to do here. We're not really doing any new math. And there would be a reasonable way to write my derivative. All right, one more. We've got 25 arcsine x over 5 minus x times the square root of 25 minus x squared. This one's kind of a classic. It's one I swear there's a problem like this in almost every textbook. We're going to do our derivatives, and then doing some simplification, we're going to be able to find a fairly nice form of the derivative here. So dy dx is 25 times, and now the derivative of arcsine is right here. So I'd have 1 over the square root of 1 minus, and instead of the x, I actually have an x over 5. So this is going to become x over 5 squared. Then I would have my chain rule. The derivative of that inner function would be 1/5. Minus. I've got a product rule going on over here. F is the x, And g is that square root, which I'll write as 25 minus x squared to the 1/2. So f prime is 1. And g prime is 1/2. 25 minus x squared to the negative 1/2 times negative 2x for the chain rule. And I can actually divide out those 2's. So when I put my product rule in place, I'm actually subtracting everything. So I'm going to put some big brackets here. I have x fg prime, so x times negative x times 25 minus x squared to the negative 1/2. Plus g times f prime, 25 minus x squared to the 1/2, just times 1. All right, let's see what we can do here. I'm going to go ahead and just kind of looking ahead at where I want to go with this. I know I could reduce the 25 and the 5, but I think I'd like that 5 in the denominator. I'm going to leave it there, and you'll see why in just a couple of minutes. Let's just rewrite that first fraction as 25 over 5 times the square root of 1 minus x squared over 25. Actually, that'll be minus a minus, so that'll be a plus. And I'm going to write that as x squared over the square root of 25 minus x squared. And now minus the square root of 25 minus x squared. That's not terrible, although I do have a complex fraction right here. But I think I can actually do better. What I'm going to do is I'm going to think of this 5 as a square root of 25. So that these are now both radicals, I can distribute this in here. So that's going to make that 1 into a 25, and it's going to cancel out the denominator there, 25 minus x squared. Notice I've already got that same denominator on my second term, which is really nice. And since both of those first terms have the same denominator, let's go ahead and get the third term to have a common denominator as well. I'm going to multiply this third term by the square root of 25 minus x squared over the square root of 25 minus x squared. So in the numerator, radical times radical just gives me 25 minus x squared up on top there. And I've now got the same square root of 25 minus x squared on the bottom, giving me a common denominator for all 3 terms. Because I have a common denominator, of course, I can distribute, or I can combine, rather. And let's do one more thing here. I'm going to change this to a plus, and I'm going to distribute the negative. So that becomes a negative 25 and a positive x squared. 25 and negative 25 are 0, and I will have a 2x squared there, all over that common denominator. And so there's my nice simple form of the derivatives. I mean, it originally looked pretty bad, but we were able to simplify quite well. All right, to finish up this section, we're going to take a look at a couple of applications where we can make use of these inverse trig functions. So in our first problem, a model rocket is launched 20 feet from an observer. Find the rate at which the angle of observation is changing with respect to the height of the rocket when the rocket is 10 feet in the air, and again when it's 100 feet in the air. So let's start with a drawing. We've got our observer over here, and then the rocket is launching right here. The launch is 20 feet from the observer, so 20 feet away. I don't know the height of the rocket because, of course, that will change over time as the rocket is launching, so let's just call it h. And then this refers to the rate at which the angle of observation is changing. So if you imagine this observer looking up at the rocket, this angle theta would be that angle of observation. Okay. Our goal is to find the rate of change of that angle of observation. So we want to find the derivative of that angle of observation with respect to the height of the rocket. So dh. The rate at which theta is changing with respect to height of the rocket. All right, in order to do that, I'm going to need an equation for theta in terms of h. So let's work on that next. Clearly the tangent of theta could be written as h over 20. But I need an equation for theta itself. So let's go ahead and take the arctangent on both sides. And so theta is the arctangent of h over 20. Okay. I can now take the derivative to get d theta dh. And again, I'll just remind you of the formulas list. For the arctangent, we would have 1 over 1 plus, and instead of x squared, in this problem the argument of my arctangent function is h over 20, so I'd have h over 20 squared. I would then have a chain rule, so times the derivative of that inner function, which would be 1/20th. Now in this particular case, I could do a bunch of algebra, not a bunch, but some algebra, to clean this up a little bit. But in fact, my final answer isn't the derivative. My final answer is the rate of change when the rocket is 10 feet up and when it's 100 feet up. So ultimately, I'm just going to be plugging in numbers for h, meaning this is probably as good a form as any. So I'm going to say, let's plug in h equals 10. And then we'll also plug in h equals 100. And the rate of change when h is 10 would be 1 over 1 plus 10/20ths would be 1/2, or 0.5 squared. And then that whole fraction gets multiplied by 1/20th. So I have about 0.04 for d theta dt here. And let's see, what about the other one? Again, I have my fraction 1 over 1 plus 100 divided by 20 would be 5, so 5 squared. Take that whole thing times the fraction 1/20th, and I have about 0.002, let's call that. So this is saying that the angle is changing at the rate of 0.04, the units of the angle would be radians, per, the units of height are feet. So the angle is changing by 0.04 radians per foot that the rocket goes up in the air. Same units here, radians per foot. And notice that when the rocket is a lot higher, the angle is changing more slowly, right? That makes sense if you think about it, right? If you're watching something go up in the air, you have to move your head quite a bit more at first. And then once it's way high up, you don't have to change your angle as you look at it very fast at all. So hopefully that makes some logical sense. All right, let's do one more application. A kite is flown at a constant height of 50 feet, but is blown horizontally away from the child holding it. Find the rate at which the angle between the string and the horizontal is changing with respect to the length of the string, when the length is 75 feet, and again when it's 200 feet. So once again, I think a picture is going to help us out a lot. This is my child holding the kite. The kite is at a constant height of 50 feet. So that's always 50. But it's being blown horizontally away, so this x value is going to change. My goal is to find the rate at which the angle between the string and the horizontal is changing. So the string and the horizontal, this angle theta, with respect to the length of the string, when length is 75 and 200. So I need another variable here, the length of the string. I'm going to call it L. And I want the rate of change of theta with respect to L. I want d theta dl. So in this case, I'm going to say that 50 and L would be what? The opposite and the adjacent? So I'm going to go with the sine of theta equals 50 over L. And so I could do the arc sine on both sides. Theta would be the arc sine of 50 over L. Now, I could work with this, but I want to talk about a slight change using a little bit of trig that might be an advantage. Did you notice up here, when we did our derivative, the chain rule spot right here, the derivative of h over 20 was really simple, right? It was just 1/20th. And that's because that h was in the numerator. I have a disadvantage down here. With L in the denominator, the derivative of 50 over L is going to be a little bit more complex. It's going to just add complexity to my problem. So I'm going to say, I actually have another option. If I don't want that L in the denominator, I could just change this and say, well, instead of sine theta, what if I used cosecant theta? Then L would be on top, and 50 would be on the bottom. I would then have theta equals the arc cosecant of L over 50. It's just a nice little algebra saving move that I really recommend. So I'm going to go ahead and say, although this is correct, I'm actually going to use this one because I think it's going to save me some work as I go ahead. So let's get the derivative. D theta dl will be, and let's see, we need the arc cosecant. Right here. So I'd have -1 over the absolute value of, and in this case, instead of x, we have L over 50. Times the square root of, and again, instead of x, we have L over 50 squared minus 1. And once more, notice that my argument was L over 50, so every place I saw an x here, I had to put L over 50 into my formula. We'll multiply all of that by our chain rule, which because of the trig function we chose is nice and simple. The derivative of L over 50 would just be 1/50th. All right, once again, we could spend time simplifying, but there's probably not a lot of point in that because all I'm going to do is plug in numbers. 75 feet for the length and 200 feet for the length. So we can do that even from the form we're in right now. If we have 75 feet of string out, I would have d theta dl is equal to, oh, let's see, I should probably put this into my fraction mode. I think it's alpha y equals, yeah, there's that fraction, makes it just a little easier to type in. I didn't do it last time, but I probably should have. I would have -1 over 75 over 50 is what, 1.5, 1.5? Times the square root of, and again that would be 75 over 50 or 1.5 squared minus 1 times 1/50th, and I'm getting about -0.0119. Same units as last time. This is the change in an angle, so that would be in radians per foot of string. And notice this time the angle is decreasing, right? The further away the kite gets, the smaller the angle is going to be. So as the more string goes out, the angle between the string and the ground will actually get smaller. We could do the same thing with an L of 200. And let's see, what am I going to get this time? -1 over 200 over 50 would be 4 times the square root of 4 squared minus 1 times that 1/50th and I've got -0.0013 about. Radians per foot. And it's the same idea as the rocket. The further away the string, or the further away the kite gets, the longer the string gets, the more gradually that angle is going to change. At first it'll change faster. This is a slower rate of change when we've got a longer string out. All right, that brings us to the end of 2K.